Let's record. Okay. So first of all, good morning to everyone. Now we are in a new week. So let's see what we have for this week. We have something different, which is fluid. So we are going to have density, pressure, Pascal principle, maybe things that you have already seen, buoyancy. I will go also from flowing fluids, so that on Friday, instead, we can move to a different topic, which is the simple harmonic motion. Okay, so this is going to be essentially lecture 28, 29, and 30. And I just wanted to remind you that you are going to find in Laulima the slides that I showed you in Zoom. And also the videos are going to be on YouTube. Okay. So let me stop share this thing. And I'm going to share these slides. This one, okay. So let me try again if I do that, okay. So solid and fluids. So first of all, no, I have this bar that is really on the top of it. So I don't even read the title. Let me try this way.
It looked good on our end. Yeah,
okay.
We don't see a bar over the top. Do you?
Yeah, I have a bar. Do you know the bar with all the menu? That it always stays in the middle, and I don't know how to make it smaller. So it always stays here. I don't know. Anyway, so density, the density of a substance of a uniform composition is defined as the mass per unit volume. I'm sure you have already seen that, and is indicated as rho. So we have mass divided by the volume. So here, because it's a mass, we have a kilogram as a unit divided by meter to the cube. Okay, so here I just give some example of the typical volumes that you might find. So for example, a sphere, 4/3 pi r to the cube, and then you might have a cylinder, so it's pi r to the square h, or you might have a cube of which is a to the cube. So the densities of gases vary greatly with changes in temperature and pressure, as you know, while the density of most liquids and solids varies slightly with changes in temperature and pressure. Okay, so fluids are indicated as liquids and gases and are materials that flow. So they are easily deformable by external forces. But a liquid is incompressible, so its volume is fixed and is impossible to change it, and will flow to take the shape of the container that holds it. A gas will completely fill, of course, its container. Now let's see a new concept, the concept of pressure. So pressure arises from the collisions between the particle of a fluid with another object. For example, the container walls, okay? We have studied the collisions. And so you remember the momentum. So we have an initial momentum of this molecule that is hitting on the container here. And then we have a final momentum. So there is a momentum change impulse that is away from the container walls. So there must be a force extended on the particle by the wall. And so by Newton's third law, there is a force on the wall due to the particle, okay? So this is what is essentially the concept of pressure. So the pressure of a fluid is also defined as the ratio of the force extended by a fluid on a submerged object or on the wall of the vessel to area. So it's the force divided by the area. And the units is Pascal. Pascal means Newton divided by meter square. And below there is an example. For example, we have 100 Newton force over 1 meter square. And so the pressure is 100 Newton divided by 1 meter square, which is essentially 100 Pascal. Here, sometimes you find that instead of Pascal, you find that sometimes the pressure is indicated in atmosphere. And here you see the formula to change from atmosphere to Pascal. So do you want to add anything, Mike? I don't know. It's up to you.
Yeah, I just wanted to point out that could you go back to the density slide?
Yes.
So hopefully people are familiar with density from chemistry and earlier science classes, but I wanted to point out that the CGS units are actually used more commonly by a lot of people than the MKS units. So be prepared to see that. And the reason is because liquid water has a density of 1 at not STP, but something close to STP. It's like 4 degrees Celsius, 1 atmosphere pressure. Okay. Then liquid water has a density of exactly 1 gram per cubic centimeter. So the density of water is the cornerstone of the metric system. It is what relates mass in the metric system to distance. So if you have 1 cubic centimeter and you fill it with water, then it will have a total mass of exactly 1 gram.
Very
Great.
good.
So I think everyone should just memorize that. You should just memorize that. And people talk about, oh, the density of this stone or this mineral is 2.6 or the density of benzene is 0.83. They're always talking about relative to the density of water. So they're talking grams per cubic centimeter. So that's something you're going to hear really, really commonly in all of your science classes.
Yes. Do you want to write it down maybe so they can take notes?
Write down, I'm sorry, write down that the density
of water
is equal to 1 gram per cubic centimeter. And a lot of times when people say, oh, the density of some substance, they'll just give a number and they won't say the units, but what's implied is grams per cubic centimeter or times the density of water. Like the density of water is used as a reference point for the density of other stuff. So the density of gold is 19.3 times the density of water, right? Yeah.
Yes, very good. Thank you so much.
Sure.
Are there questions about this part?
Okay, so yeah, so moving on to pressure now, right?
Yeah. So then let's see another example. Someone steps on your toe, extending a force of 100 Newton on an area of 1 centimeter square. What is the average pressure of that area in atmospheres? So first, we want to change from centimeters into meters. So we have 1 centimeter. To do so, we do divide 1 centimeter square. To do so, we do 1 meter divided by 100 centimeters to the square. And then this comes out to be 1×10⁻⁴ meter square. Okay, so this is just to change from centimeter square to meter square. Then we use the definition of pressure. And so we have P, the pressure is force divided by the area. So 500 Newton divided by the area in meter square that we just found out, 1×10⁻⁴ meter square, which comes out to be 5×10⁶ Newton per meter square. Now we need to, is asking in atmosphere. So what we do, we have to make the conversion. So 1 atmosphere divided by is essentially 1.013 10⁵ Pascal. So this is what we are going to do. We are going to multiply and divide in a way that at the end we find 49 atmosphere. Okay, so you see that in this way we get rid of Newton per meter squares, we get rid of Pascal, right? Unfortunately, if I don't do like this, you cannot see where I'm pointing. So with this, you remove Newton per meter squares, and you can say that 1 Pascal is 1 Newton per meter square. So this is not going to change anything, and you get rid of these units that you don't need. And then you want here atmosphere, so 1 atmosphere, and you want to get rid of Pascal, so divided by this. And you end up with only atmosphere, which is what we want. Very good. Then we have the pressure and the Pascal's principle. So the pressure in a fluid increases with depth due to the weight of the fluids above it. So essentially, it's pretty simple to understand this concept. So the more you go deep, the more in this fluid, the more you are going to feel more pressure. And probably you have seen it also when you get into the ocean, right? If you go deep into the ocean, what you normally have to do when you dive is to essentially you want to close your nose and breathe out the water, because otherwise you're here are going to feel strange. You're going to feel strange, like there was a, you know, a change in pressure. So indeed, there is a change in pressure, because if you go down, you have all the weight of the water above you that is going to put a pressure on your body, right? So it's exactly this concept. So if a fluid is at rest in a container, all the portion of the fluid must be in static equilibrium. Okay, so if the fluid is at rest, everything is in static equilibrium, which means that all the forces, you know what static equilibrium means. So all the forces, the sum of all the forces applied is essentially equal to 0. So they are going to be in equilibrium. So here we have that all the points at the same depth must be at the same pressure. Otherwise, the fluid will not be in equilibrium. And so if you get any position here, all the points in that position has the same pressure. In this case, we have 3 external forces that act on the region of a cross-sectional area A. So we take one certain area A, and what we have essentially the external forces, which are the atmospheric forces, which indicate with POA. And then we have the weight, okay? So we have mg, and then we have the normal force, because as you know, if you apply a force in this liquid, the liquid is going to give you, for the third Newton law, is going to give you another pressure opposite in direction and of the same magnitude. Okay, so here we have that the sum of the force is equal to 0, and this one is our PA, which is the normal force, so the pressure multiplied by the area, a cross section of this object, minus mg, because the weight is going in this direction, right? Always perpendicular and always to the center of our planet. So minus mg minus P naught A, where P naught A is again the atmospheric force. This has to be equal to 0. So the mass we know from the density that we saw before, that is the density multiplied by the volume, right? So it's the opposite of this equation. So mass is rho v, and the volume in this case we know that is AH, so the area multiplied by the height of this cylinder. So what we have is that PA, our normal force, is equal to P naught A plus rho AGH. So the pressure is equal to the atmospheric pressure plus rho GH. Okay. Why is important this information? Because PO is a normal atmospheric pressure, so we know the value of P naught, sorry, which is 1.013 10 to the 5 Pascal. Okay, and so because of that, we see that the pressure does not depend upon the shape of the container. It doesn't depend on the shape of the container. So the pressure here in point A is equal to the pressure in point B, which is equal to the pressure in point C, which is equal to the pressure in point D. Because all of this pressure you calculated with the normal atmospheric pressure, which we know, then it depends on the rho, which is the density of the liquid. So of course depends on the density of the liquid, but then we have G, which is a constant, and H, which is exactly the location. Okay, so it only depends on the density and on the location. And if the fluid is the same, so the density is the same, then it only depends on the depth in H. Okay, so that's why this equation is important. So let's see another example. Find the pressure of 100 meters below the ocean surface. So we are going to use the formula that we just saw. P is equal to P naught, which is the atmospheric pressure, plus rho, that is the rho of the water, H2O, GH. Okay, so we have the P is 1 times 10 to the 5 Pascal. Then rho of the water is 10 to the 3 kilograms per meter cube. Then G is our 9.8 meter per second square, and H is 100 meters. The units are all good to be used together. So if we remove all these things, we find 10 to the 6 Pascal. Okay, which is 10 times more than the atmospheric pressure. So that's why when you go deep down into the ocean, you see that the pressure is different and you have to somehow release your ears. So
In fact, I think a lot of divers, hi, Dr. Mindy. So a lot of divers memorize that every 10 meters down that you go, you add one more atmosphere of pressure on Earth, right? So
yes,
every 10 meters down in the ocean that you dive, or a lake or anything, yep, it's one more
yes.
atmosphere. So in the United States, of course, no one knows what a meter is, so they remember 30 feet. Every 30 feet down that you go,
Yeah,
you add another atmosphere of pressure. Great, thanks.
very good. So let's see another problem. We have the surface pressure on the planet Venus is 95 atmosphere. How far below the surface of the ocean on Earth do you need to go to experience the same pressure? The density of seawater is 1,025 kilograms per meter cubes. So in this case, we are going to use the pressure is equal to the atmospheric pressure plus rho g d. In this case, we know that we are looking for a place, we are looking for D, right? Which one is the deep? Which one is our D or H, as we call it before. So here we want to have 95 atmosphere. Here is 1 atmosphere because it's P atmosphere plus rho GD. Now rho GD is going to be equal to 94 atmosphere, which means this, if we transform it in terms of Newton per meter square, then we have the rho is provided, and is this one. G, we know how much is G, and then we can find D. So because now we brought it as Newton per meter square, we can go on and do all the simplification, and we find that D is equal to 950 meters. So to be able to experience the same pressure that you have in the surface of Venus, you need to go deep into the water, 950 meters. So yeah, it's very intense, I would say. We don't want to go to Venus. Okay.
Yeah, that's a huge problem for the spacecraft, right? The spacecraft get crushed like little aluminum cans.
Yes.
Yeah, because it's hard for us to build objects that can withstand that kind of pressure for very long. Yeah, it's like a diving bell, right? Essentially.
Yes.
Yep.
So let's see another important application of fluids, which is the Pascal principle. So this is very, very important. And as I said, it has lots of applications. So a change in pressure applied to an enclosed fluid is transmitted undiminished. It's very difficult to pronounce. How should I pronounce this? Undiminished. Undiminished.
Undiminished.
Undiminished.
Undiminished.
Okay, you got it. Thank you, Mike. To every
Sure.
point of the fluid and to the walls of the container. So
And
here
could I just add also, we just learned that pressure increases with depth, right? So for the moment, when you look at that diagram on the right, we're kind of ignoring gravity here, right? We're assuming that the internal pressures of the fluid are just much, much, much bigger than any additional little increase that might be caused by this additional height difference. So,
yes.
Yeah. Okay. So if it's easier, just ignore it. If it's easier for our students to think about it, ignore gravity or pretend this is in the space station or something. Yeah. Thanks.
Yes. And so in this case, we have the hydraulic press is an important application of the Pascal principle. So in this case, we have that the pressure is the same between the ratio from F1 to A1. You see here the force F1 and A1 is the same of F2 over A2. So because we have that A2 is much, much bigger than A1, and because we just say that the pressure is transmitted and undiminished. So what we have is that the pressure here is the same as the pressure here. But here, because you have A2 that is way bigger than A1, what you are going to have is that F2 is going to be way bigger than F1. So before that, I want to show you this. Because of what we just said, so assume that we have a force of 500 Newton, which is about 110 libs, is applied to the smaller piston in the previous figure. For each case, compute the force on the larger piston if the ratio of the piston areas are 1, 10, or 100. So here, if we have the F2 that is 500, if we have the same F1, which is 500 Newton, but if we have that A2 is equal to A1, so the ratio is 1, essentially what we have is that F2 is 500 Newton. So you apply the same force to F2. But what you have here, in case you have that A2 is 10 times bigger than A1, also F2 is going to be 10 times bigger than F1. So you're going to have 5,000 Newton. And if you have A2, which is 100 times bigger than A1, what you are going to have is that F2 is going to be 100 times bigger than F1. So you're going to be a force of 50,000 Newton. So that's why I said before is a very useful tools, this one, because as you see, you apply a smaller force here, but because you make this area much bigger, you are able to obtain a huge force there. So delta P at point 1 is equal to delta P at point 2. So what we have is F1 divided by A1 is equal to F2 divided by F2. So F2 is equal to A2 divided by A1 multiplied by F1. If we remember about the work, do you remember? Work was the force multiplied by the displacement. So the work done pressing the smaller piston 1 equals the work done by the larger piston 2. So F1 D1 is going to be equal to F2 D2. So what you see here is that, of course, when you apply F1 to A1, you have a big displacement. While here, you are going to have a much bigger force, but you are going to have also smaller displacement. So you,
Sorry, go ahead. Go ahead.
Oh, I just wanted to read this. Using an hydraulic lift reduces the amount of force needed to lift the load, but the work done is the same.
Great. That's exactly right. And we call this a mechanical advantage, right? When you use some sort of device that allows you to reduce the amount of force needed to accomplish a task. So it turns out in this particular case, the mechanical advantage is this ratio right here. So that's the mechanical advantage right there, right? However, you don't get something for nothing. So the amount of energy it takes to accomplish the task, like lifting the truck, is the same whether you use the machine, in this case, the hydraulic lift, or not. Yeah. In fact, oftentimes the amount of energy it takes is even slightly more because there's friction and other stuff in the system. And so that friction acts over a longer distance with this bigger displacement. Yeah. But that's all right. The force advantage is so advantageous for us as humans that we were happy to take it, even though there's no energy or work advantage.
Okay, very good. So let's see another example. So in the previous example, for the case A2 over A1 equal to 10, this one, okay, we had the F1 500 Newton and F2 5000 Newton. It was found that F2 over F1 is equal to 10. If the larger pistons needs to be raised by 1 meter, how far must the smaller piston be depressed? And so here we are going to use the conservation of the work. And since the work done by both pistons are the same, and remember we have work done by the first pistons is F1 D1. Work done by the second piston is F2 D2 because the work done is the same. So we can write D1 is equal to F2 over F1 D2. And this needs to be equal to, D1 needs then to be equal to 10 meters because F2 over F1 is 10 and D2 is 1 meter. So as you see, at the end of the day, these problems are pretty much simple, I would say. So let's see another example. Depressing the brake pedal in a car pushes on a piston with cross-sectional area of 3 centimeters square. So the only thing, you need to be that you really need to be attention to are the units. These are the things that I would say this more complicated because the formulas are really simple. So the piston applies pressure to the brake fluid, which is connected to 2 pistons, each with area 12 centimeters square. Each of these pistons presses a brake pad against one side of a rotor attached to one of the rotating wheels. See the figure for this problem. Okay. So those are the pistons. This is the brake paddle. Okay. When the force applied by the brake pedal to the small piston is 7.5 Newton, what is the normal force applied to each side of the rotor? Each side here and here of the rotor. So here we have another piston and another piston. So the pressure of the fluid is force divided by the area. So pressure, normal force divided by the area of the brake pad piston A. So the normal force applied to each side of the rotor is going to be A, the area divided by the area of the brake multiplied by FB. So we are going to have the area (12 centimeters square), which is our piston area.
Right. Yeah, it doesn't look like it, but it's actually this little area right here.
Yes, it looks smaller than this one,
I
but
know, yeah, for the good way it's drawn. Yeah.
yeah. While this one is the one of 3 centimeters square. Okay, so is AB. Okay, so we have 12 centimeters square divided by 3 centimeters square, multiply by the force that we apply, which is to the small piston, which is 7.5 Newton. So the normal force is 30 Newton.
Great. And by the way, could I add a couple things about
Yes.
power brakes in cars? Okay, so as you can see, there's a fluid, right, that has to go in this little tube. So two things. One is if you ride your brakes down a long mountain, then there's so much heat generated at this point of contact here that it will make the fluid that's touching the back of the piston boil, right? So we try and use a brake fluid that has a very, very high boiling point, but even still, it gets up to hundreds of degrees and it starts to boil. And once it becomes a gas, then all of a sudden it can compress, and this Pascal's principle no longer applies. And then you compress your foot all the way down to the bottom, and nothing happens with your brakes because it's no longer a liquid inside those brake lines. It's now a gas. So the cure for this, if you don't die and crash, the cure for this is to just let the stop using the brakes, somehow bring your car to a stop and let them cool off. And as that fluid cools off, a gas cools off, it turns back into a liquid, and then your brakes will work again. But the hard part is not crashing and dying in that interim part. The other thing is, if any of you have seen action movies and someone wants to sabotage someone's brakes, what do? They come in here and they cut this fluid line, and then the fluid drains out, and then the person, when they press their brakes, nothing happens. Thanks.
Very cool. Very cool. Okay, so here we have a question. Suppose that you place an extended object in the water. How does the pressure at the top of the object relate to the pressure at the bottom? And this you should know. So is the same? We say no. The pressure is greater at the top, of course, no. The pressure is greater at the bottom. And we know that because there is more fluid here that is pushing. So the weight of the fluid is bigger on this area here. And so we have a much bigger pressure. We have more water on the top of us. So this is called the buoyant force. And what is the magnitude of the force? So we have here, imagine this object, which is immersed into this fluid. Let's assume is water. What we indicated here is the weight. We have the buoyant force, which is going up, and then we have P1A and P2A. So let's see what these are. So P1 is the pressure that the object feels here in this location, and P2 is instead the normal force of the object generated by the water. So the buoyant force is defined as P2 minus P1 multiplied by the area. But because we know that P2 is P1 plus rho GH, remember, we found it before. So what we have is that B is P1 plus rho GH minus P1. So we can essentially remove P1 from this equation, and we are going to have rho of the fluid GHA. So HA, you know, that is our volume. So we are going to have rho of the fluid G volume. So any object completely or partially submerged in a fluid is buoyed up by a force whose magnitude is equal to the weight of the fluid displaced by the object. And indeed, you see here rho of the fluid G and V multiplied by the volume. Do you want to add something about this, Mike?
This final formula result here, I think, is sometimes just called Archimedes principle. Yeah.
Yes.
Yeah. Yeah. So if this formula is, oh, there it is. Okay. Yeah. That formula is the mathematical equivalent of that statement called Archimedes principle. Okay.
Yes. And also the magnitude of the buoyant force always equals the weight of the displacement, the displaced fluid. So B, the buoyant force, is rho of the fluid, Vg, which is also equal to the weight of the fluid. So the buoyant force is the same for a totally submerged object of any size, shape, or density, and is exerted by the fluid itself. And whether an object sinks or floats depends on the relationship between the buoyant force and the weight. So here, examples of Archimedes principle for totally submerged object. So the upward buoyant force is B, rho of the fluid, G, the volume of the object. And then we have the downward gravitational force, which is the weight, right? Our mg. M is rho of the object, G, V of the object. So you already see here how similar those are. And really what it changed is the density. And indeed, the net force is the buoyant force minus the weight, which is equal to rho to the fluid minus rho of the object multiplied by G, the object. So depending on the direction of the net force, the object will either float up or sink. So essentially, is the rho of the object is greater than the density of the fluid, of course, this force will be negative, which means that the object will go down, like in this case, okay, will go down. While if instead the object density is smaller than the density of the fluid, this component will be positive, this force will be positive, which means we're going to have an acceleration that goes up, and so the object will float. So the object is less dense than the fluid. This is essentially saying exactly what I said already. The object is less dense than the fluid, then the object experiences a net upward force. While if the object is more dense than the fluid, then the net force is downward, so the object accelerates downward. So the object is in static, if the object is in static equilibrium, means that the upward buoyant force is balanced by the downward force of gravity. So the volume of the fluid displaced corresponds to the volume of the object beneath the fluid level. So in this case, we have rho of the fluid, G, V of the fluid is equal to rho of the object, G, V of the object. G is present in both parts of this equation, so we can remove it. And so we have that the ratio, if we just do the ratio of the rho of the object divided rho of the fluid is equal to the ratio of V of the fluid divided by V of the object. Do you want to say something?
How can you tell? Yeah, right. So this is what I like to call the iceberg formula, right? It's talking basically what fraction of this floating object, what fraction of the floating object's volume will remain submerged when the object is floating in equilibrium. So this displaced V is just the part that is under the surface, whereas the object V is the entire object. So it's the whole thing. Yeah.
Yes.
And note, yeah. So if so for the example of an iceberg, the density of ice is about 0.9 and the density of seawater is about 1, right? So that means that 90% of the iceberg will remain below the surface of the ocean and 10% will stick out.
Yes, very good. Yeah, so here in this case, as you see, is in static equilibrium because it doesn't move from this direction, right? It's floating. And it's so because it's floating, you can assume that this equation B is equal to the weight. But as Mike point out, so the V here you have to use the V of the fluid that is submerged. While here you need to pay attention because it's the entire object. This is very important.
Yeah. V fluid here, that subscript fluid refers to the amount of displaced fluid. It's the volume, pardon me, of displaced fluid. Yeah, so it's an unusual use of the word fluid there. Yeah.
Yes.
Good. Thanks.
Okay, so let's see immediately one example of the floating frog. So a frog is an hemispherical pod, finds that it just floats without sinking in a fluid with density 1.35 grams per centimeter cube. If the pod has a radius of 6 centimeters and negligible mass, what is the mass of the frog? So here, since the frog floats, the buoyant force must be equal to the weight of the frog. And then from Archimedes' principle, the weight of the displacement fluid equals the weight of the frog. So we have the rho of the fluid multiplied by the volume multiplied by G is equal to the mass of the frog multiplied by G. Or mass of the frog is equal, we can remove rho G from this equation because it's left and right. So the mass of the frog is equal to rho of the fluid volume. So rho of the fluid is 1.35 gram per centimeter cube, while here the volume is 1/2 4/3 pi r to the cube, because it's a semisphere. So it's half of the sphere. So 1/2 of a sphere, the volume of a sphere of a radius, 6 centimeters. So we do all the calculations and we find that the mass of the frog is 611 grams, which means 0.611 kilograms. Do you have other things to add, or I can go on?
I don't know what kind of liquid has a density of 1.35.
I don't know.
That is friendly to a frog. I don't know what the. All right. I want to just add that most
maybe
animals,
olive oil. I don't know how much.
maybe I'll. Who knows? Most animals have, or swimming animals, right? Like fish, for example, they have a little air bladder inside, also called a gas bladder, inside their body, and it's basically a little balloon full of air or gas. And they can squeeze it to make it smaller, which increases the density of the body of the fish, and the fish will dive. Or they can expand it, making it larger, which decreases the mean density of the fish, and the fish will automatically rise. So fish generally don't have to swim downward or swim upward with effort. They can just adjust the size of their little internal gas bladder, and then they automatically rise or fall. Or if they go right in the middle, then they're neutrally buoyant. So when you look at a fish that's just sort of hanging out at a constant depth, that's what they've done. They've adjusted their gas bladder, so they're neutrally buoyant. Great.
This is super cool. I didn't know that, Mike.
So that's what this frog. So this frog doesn't have a gas bladder. He has lungs. We can do this, right? You can do this in a swimming pool too, right? So everyone who's listening,
yeah.
Right? You probably know this. Take a deep, deep breath, and you'll float. Force all the air out of your lungs, and for many of us, will sink. And you can fill your lungs to just sort of a middle amount, and you'll be neutrally buoyant in the swimming pool. Great.
Very good. And then here, I mean, we have just a few minutes. So in these few minutes, I put the manometer, which is a U-shaped tube that is partially filled with liquid. So here is open to atmosphere. Both ends of the tube are open to the atmosphere. And so you can, when you attach something, like in this case, you attach gas here. So if there is a pressure difference between the gas and the atmosphere, a force will extend on the fluid in the U-tube, and this change the equilibrium of the fluid in the tube. And so then you are able to measure the pressure. So the pressure at the point B is the pressure of the gas. Okay, so as you see before, it was in equilibrium. You see, so we have a certain level, and here we have it opens. So in this case, we just put the pressure of the atmosphere. And then after that, you attach the gas here. So you have that, because the gas is attached, you have that point C is the pressure in C is equal to the pressure of the atmosphere. And also you have that PB is equal to PB first, right? Because we say that doesn't really depend on the shape, but if they have at the same deep, the pressure is the same. So the pressure at point B is the pressure of the gas. So what we want to calculate, that is PB is equal to BB first, which is equal to PC, the atmosphere, or at point C, plus rho GD. So in this case, what we have PB minus PC is equal to PB minus P atmosphere, which is equal to rho GD. So I simply bring PC in this other side of the equation. And so P gauge is equal to rho GD. And in this case, the gauge pressure is defined like the pressure minus the atmospheric pressure.
Right. So when you measure the pressure of a bicycle tire or a car tire, right, that what the gauge that you're using is actually telling you the difference between the pressure inside the tire and the ambient atmospheric pressure outside. It's not telling you the absolute pressure inside the tire. Yeah. Yeah, it's telling you that difference.
Yes. And then a similar concept is with the barometer. So the atmosphere pushes on the container of mercury, which forces mercury up the closed inverted tube. And so the distance D is called the barometric pressure. So here again, we have this, and we have PA is equal to PB, which is equal to the atmospheric pressure, and PA is rho GD. So the atmospheric pressure is equivalent to a column of mercury of 76 centimeters tall. And with this, I have finished with the...
Yeah, that's sea level, 1 atmosphere. Oh, this is perfect. So this is basically lectures 28 and 29. So hydrostatics as well. Great.
Yes.
And anything dynamic will be next time, which is number 30, which is perfect.
Okay.
Right. So I'll just add one quick thing, and that is so this is atmospheric pressure at sea level, right? Which we sort of define as 1 atmosphere. As a result, it goes by all of these names. It goes by 76 centimeters of mercury. It also goes by the name 760 millimeters of mercury. And millimeters of mercury is the same thing as Tor, right? Named after Torricelli. And then sometimes, especially in America, we like to use water. So instead, if we put H2O in here, then you can get other things like, I don't know what the conversions are, but you can get centimeters of H2O, you can get millimeters of H2O, you can get feet of H2O, inches of H2O, which is what I have on my cell phone when I look at the barometric pressure. Oh, and actually on my cell phone is inches of mercury. So right now the pressure outside is about 30 inches of mercury, 30.1. Right? It's a pain. This is just a pain. Fortunately, you just have to look it up every time you want to convert between pascals or atmospheres and one of these other ones. Whether I haven't even mentioned bars and millibars. So weather reports still use a lot of these. Chemists like to use atmospheres. Doctors like to use millimeters of mercury for your blood pressure readings. Whatever discipline or scientific area you go into, you'll end up just learning to memorize the commonly used pressure units in that particular discipline.
Okay, are there any things from the chat that you want to emphasize or?
There was one interesting question, which is pressure a vector? That's actually a really interesting question. We generally use it as a scalar in all of our formulas, right? We think about P is equal to F over A, or we think of ideal gas law, right, which we haven't talked about yet. But we generally use it as a scalar. However, the force that results from a pressure or a pressure difference does have a direction. So that net force, like the buoyant force, for example, is a vector. So forces always have a vector direction.
Okay.
Great question. Yep.
Very good. So, okay, the time is up and yeah, the lecture is up. So have a wonderful rest of the week and see you on Friday.
Thanks, everyone.
Thanks, everyone. Bye-bye. So I'll stay online.
Okay, great.
Thank you. Have a wonderful day.
Oh, okay. Everybody's gone. It's just us chickens. So, Julia, if you want to take a quick break, I can hold down the fort for a few minutes. I wanted to chat with Veronica for a sec anyway. Would that sound good to you? Otherwise, you're welcome to listen in too. It's nothing secret or anything.
Okay, sounds good. Thanks.
Great. Veronica, you can tell I love this subject, right? This is just
I can tell.
It's one of the fun subjects, right? It's like it's so much more exciting than like rotation. Like I mean, all right, I'm excited about angular momentum too, but still, this one is so relevant to daily life that I mean, if our students aren't turned on by this, I don't know what would excite them. All right, I was just going to point out that the recitations are, I mean, we're still going. I have a problem set ready for this coming week. I guess we're kind of lucky that the upcoming Friday holiday doesn't really disrupt us, but all right. All right, here's one thing. The very last week of the semester is May 2nd through 6th, but technically I think May 4th is the last day of classes. So May 5th and 6th are both study days, right? So that means that Tuesday and Wednesday of that week are instructional days, but then Thursday is not. So I'm thinking about what we should do for recitations for that week. What I could do is just, instead of having an actual, and then our final exam is on a Monday. It's not at the end of finals week, it's at the start of finals week. So I'm thinking, instead of having an official recitation problem set on the thermo material of that era, of that time, we could do like a review day. We could just cancel recitations that week. We could.
Yeah, I think we could do a review day and cancel the recitation. What do you think?
Yeah, I may be, right? Or I can do like a problem set that is just a bunch of review questions from the whole semester, or but have it be optional, right? Instead of being due, because it's, when will we make it due? We have to make it due on like the Monday of the final exam, but the final exam's at like 9:45.
Yeah. No, I think because that's going to be the final and it's a pretty busy week that time because they have the finals and stuff. If we do a review, they will really appreciate that without giving, additional things, I think. But
this content, we might even choose to omit some of this from the final, maybe, right? Some of this very last stuff, entropy, second law of thermo, heat engines, Carnot cycle. We could just go through ideal gas law, or potentially ideal gas law plus I don't know. We can think about it. Like the recitation of the prior week is going to be temperature, heat, specific heat capacity, latent heat, and phases, and phase diagrams. Okay, so that'll be the last week of April. recitation week.
Yes.
And then everything from ideal gas law onward, it doesn't get its own proper like full week of class. So, all right, well, it's something to think about. It's far enough in the future. We don't need to decide right now, but
yeah, but I would be like, yeah, sometimes it's better to help them out a bit doing some more review,
yeah,
rather
right.
than,
Yeah,
so yeah,
maybe
but it
so.
depends on you what you think, because I'm fine either way. I'm fine.
And then the other thing I've just been having, like, I've been having thoughts about maybe we should just cancel recitations for the rest of the semester or something. I don't know. I think they'll get grumpy. I'm just getting so tired of like dealing with all of the attendance sheets, and then
So I think
some
if we
students get marked
cancel
absent.
them completely, they are going to be a bit mad.
Yeah,
But
maybe so.
it wouldn't be bad if we decide to
Well, one thing I did last semester was toward the end of the semester, because it seemed like the students were so grumpy that they had to appear in person, right, all the
yes.
time. And some of them, I think, are just annoyed by that. Some of them don't need it, right? There'd be some students who just finish really fast and just sit there with their arms crossed, right? And in the recitation time, I think, so what I did last semester was I actually tried a couple of weeks making attendance optional, where we had a problem set, but I said, okay, everyone
But,
can,
if
attendance
you
is
make it
optional.
optional,
Yeah. But
you are
you know
not
what happened?
saving everything. You don't save anything, because at the end of the day, you have to prepare for that, and you have to
That's right.
prepare with a
That's right.
research.
It was the same amount of
I
work for me. That's
yeah,
right. And the
no,
attendance was somewhere between like 1 to 5 students per session, right?
yeah.
So
No, you know what we could do? We could say that we had how many recitation we have? 3 recitations left.
let me see here.
We
I think
might
there's
say
1, 2, 3, 4,
next
4 more.
recitation, 4 more.
4
Yeah,
more plus that half week in May.
yeah.
So
So
4 and a
you
half,
might
4
say
plus.
you might do it this week, this recitation this week, and say we decided that it might have been too much work on your side, an extra thing on your side that probably is better if you, no, probably is better, but no, I wouldn't say, actually, I wouldn't say that much. The less they know, the better it is. I would simply, if you want to not do any more recitation, at the next recitation, you just say, this is the last recitation we have. We decided that this is the last recitation, and that's it. And we modify the calendar, and from now on, we show another calendar without recitation. So you need to tell them once they are there, right?
Yeah.
If you want, you can do it. At the end, you are cutting 3 recitations.
Let me
Because
think it over.
it's not a big deal. To me, Mike, honestly, is not a big deal, because next year we decided we are not going to have recitations at all. So
That's right. That's right.
next semester. So if we decide to have 3 less this semester, it's fine. If it helps you, do what helps.
It would help me, but yeah,
Yes.
I'm all right. Well, let me think about it.
Yeah,
And,
and
yeah, I've been toying with different modes, different possibilities that might be good for the rest of the semester. But all right, we'll see how this week goes, and we'll see. Yeah.
We could also like keep the recitation sessions and just have the LAs run them. So it takes the pressure off of you guys to have to make the material, but like maybe not even have them be recitation sessions, but just like Professor, you were saying that you used to hold time for students to be able to come and ask questions and stuff like that. Cause then the LAs could keep their hours. The students who want the support could still come, but you don't have all the rigmarole of attendance and preparation and all that.
yeah,
Last semester, for example, we had 2 weeks where there was a holiday in the middle of the week. So for those weeks, we said, all right, either we had no problem set and the recitation times were just drop-in help hours, right? They became drop-in help hours. Or there was a problem set, but we said, all right, this problem set is still due at the end of the week, but attendance is optional. You no longer need to come. And if your recitation would normally be on the holiday, just come to one of the other ones if you wish.
Yeah.
And the attendance, I was just telling Veronica that the attendance really plummeted though in those weeks. Whenever attendance was optional, but there was still a problem set, it was really only between like 1 and 5 students who would come to any of those.
I see.
Really small, and we still had to show up and we still had to do it.
Yeah, right.
Well,
I see.
Yeah, so, Mike, I feel like it's too much work, as we said, and as we discussed it. And at the end of the day, I like what Julia was saying, that we could, you know, have those hours for the students to just show up and ask to the LAs for some help in some particular topics. And so they're not going to feel neglected, because if they want to have support, they can have support. And at the same time, they are going to feel relieved because they don't have to show up to do the recitation. So I think it's a sort of win-win. You know, the student can get the support if they want it, but they are going to be released from the last few recitations in a moment where they have to study for finals. They have lots of things going on.
Right.
So nobody's going to be upset with you because they want it to be a recitation. No, I want the recitation.
Well, you'd be surprised, actually. A lot of them are like, you know, I paid all this tuition for instruction. And so I need to have this instruction.
So, and they can have instruction because indeed those hours, they are going to be dedicated to them with the LAs. You know?
Yeah, and we could also have it be like review sessions, because something a lot of people were asking about on the survey was like the LAs the week or even 2 before finals. You know, we could just have them be sessions to go over the material and like help them understand what they need to know for the exam.
Yes. So
I think
them, instead of recitation session, we call them review sessions where they can get help and support. And yeah.
So on I think Tuesday, May 3rd and Wednesday, May 4th, for sure, I think that's what we'll do. Instead of trying to cover that last little bit of thermo, I think that we should maybe, you could still give a lecture on it if you want, but I think we'll cut that out of the final. And instead of giving homework on it, and instead of having a recitation on it that week, for sure, May 3rd and 4th will just be some sort of like review hours, right? And attendance will be optional, and the LAs can, and we could talk more about what shape that'll take, right? I'll think about the rest of April.
Okay.
I'll think about the rest of April. Yeah.
Yeah. Just know that, Mike, we are on your side.
Well, thank you. I appreciate that. Yeah, I'm kind of dying here. Yeah. The good news is Saturday was fun.
You're too important. You can.
I ran the Manoa experience table over on the grassy mall on Saturday, and that was fun. We actually had a huge turnout, lots of visiting families from the mainland.
Nice.
Yeah, it was really good. Yeah, it's nice to see our sister departments too. So we were between math and chemistry. Yeah. All right. Well, hey, thank you very much. I'll get back in touch if I have more updates.
Yes.
So, oh, Julia, let me make you a host. And
bye-bye. Ciao, Julia. Ciao,
Great.
Mike.
Bye, Veronica.
Thanks a lot.